Just a few centuries ago, world maps were on paper, filled with terra incognita, poorly described or unexplored shadowy areas. Virgin or hard-to-reach territories, often located in dense forests, high up on the continents or beyond the oceans, remained out of our reach. But today, every corner of the globe has been drawn and mapped by humans, who explore them, and by satellites that, all around our planet, can reveal even the smallest details to us. And yet, the map of the world has become much larger than it used to be, because we have discovered that beyond the borders of these maps, if we just lift our eyes a little from the ground, above us is where the cosmos begins. So, by turning our eyes to the vast sky, we embark on a titanic endeavor, mapping space and drawing maps that reveal to us the large-scale structures of matter and its distribution in the universe. And just like the first explorers who let themselves drift and glide along the surface of unknown rivers to discover new lands, you will see, strangely enough, that in this unfamiliar universe, we too will have to follow streamlines to draw its boundaries. Without further delay, let's leave our planet to drift into this ocean of emptiness that surrounds us. And now, every second, we are moving thousands of light years away from our world, until we finally take in, at a single glance, our galaxy, the Milky Way. This gigantic structure, a swirling mass of gas and dust, home to some 300 billion stars and spanning 100,000 light-years across, is, on the scale of the cosmos, it's little more than a part of a much greater whole, a small spot on the map of the universe. Because these kinds of objects, galaxies, whose shapes and sizes can be extremely varied, are found in every direction, everywhere we look, and they cluster together. Thus, the Milky Way, just like the Andromeda Galaxy, located 2.5 million light-years away from us, is part of a coherent group containing about 50 other galaxies, all bound together through space by the force of gravity, and called the local group, which, in terms of volume, is to the observable universe what your neighborhood is to the scale of an entire continent. Although it stretches over about 7 million light-years, our local group is a dwarf in space in terms of mass compared to other galactic gatherings, such as the Virgo cluster, which, though only about twice as wide, contains 300 times more galaxies. In this image, which is 10 million light-years wide, each white spot represents at least one or even several galaxies. Yet, as impressive as it is, with its roughly 1,300 galaxies, the Virgo cluster, just like our local group for that matter, is itself only a subset of a colossal structure, the Virgo Supercluster. A cosmic giant with a staggering estimated size of 100 million light-years in diameter, containing around 10,000 galaxies spread across about 100 different clusters. And in their work mapping out this gigantism, cosmologists long believed that this impressive gathering of galaxies was, in a way, the last continent to explore. The ultimate little terra incognita. Not that everything stops there, because obviously, beyond this supercluster, space itself continues, on even larger scales in all directions, up to the edges of the observable universe. And at this scale, we can see galaxies together forming the pattern of a vast, seemingly limitless cosmic web. We've already talked at length about this web-like structure that the universe takes on at large scales in a previous episode. If you're interested in the topic, I'd recommend watching it. The thing to remember here is that if these formations of galaxies into superclusters were long considered the end of terra incognita, it's because beyond their scale, the fabric of the universe becomes homogeneous. The millions of other superclusters that we can observe there don't seem to be part of larger structures. No coherent and recognizable galactic structure seems to exist above that scale. And in that sense, with them, we thought we had reached the second-to-last line of our cosmic address, the next one being that of our observable universe itself. As if these superclusters were to our universe what a continent is to our planet. Until we discovered, about 10 years ago, that the Virgo supercluster is just a small part of an even larger structure, and which was named Laniakea, in tribute to the Polynesians who explored the vastness of the Pacific Ocean, navigating by the stars. And in their language, this term means the immense celestial horizon. Within Laniakea, in a space 500 million light-years in diameter, we have counted 100,000 galaxies of comparable size, if not larger than ours, and millions of smaller ones. If you could move far enough away to take in this absolutely enormous structure at a single glance, then you could see Laniakea stretching across about 5% of the diameter of the observable universe itself. The discovery of this monumental cosmic structure began in 2013, when studying the movements and dynamics of the flows of about 8,000 galaxies relatively close to us, it was realized that they all seemed to be drifting at the same time, and at the with the same strength of a current within the same cosmic basin of attraction. And by diving into the mass of collected data, we discovered, nestled within, the traces of an unexpected pattern, galactic flow, revealing to us the shape of a slightly rounded monumental cosmic structure, one of the largest and heaviest in the known universe, Laniakea. Our galaxy, the Milky Way, is located on the outskirts of this immense structure, weighing 10 to the power of 17 solar masses. A number so large it likely means little to you. To try to get a sense of it, consider that the Virgo Supercluster accounts for barely 1% of the total mass of the Laniakea. To put it another way, Laniakea is to our local cluster what an anvil is to a feather. But perhaps the most astonishing thing isn't that, because if there's one thing to remember here, it's that the boundaries of this galactic supercontinent were revealed to us through the study of the flow of matter in space-time. Thus, as these models show, these cosmographic maps give us clues about the distribution of matter in the universe, while also revealing the presence of cosmic basins, where matter flows from low-density areas toward those where matter is most concentrated. They allow us to see invisible boundaries, whose limits are defined by the movement of galaxies on large scales, by the direction of their flow, which, under the influence of gravity, stream along and follow the shapes of the cosmic landscapes they cross. In these models, we can see what look like watershed lines, whose paths are not controlled by the terrain, but by the gravitational pull exerted by all the surrounding large structures. And based on the dynamics of these lines that wind and follow, in a way, the contours of a spacetime that is curved or shaped by the presence of large amounts of matter, we are able to draw the outlines of coherent structures, ever larger in scale, such as Laniakea, on whose scale galaxies are little more than leaves, carried along by the force of powerful underlying currents, tumultuous torrents, whose cosmic flow follows the shapes of space, curved by the presence of galactic clusters and mysterious dark matter. Here, in this other model created by Hélène Courtois and her team, you can see vectors forming that illustrate the direction of the cosmic flow, the path taken in space by each small colored dot, which corresponds to one or even several galaxies belonging to Laniakea. And by assigning different colors to the trajectories of these galaxies depending on the basin of attraction to which they belong, some of these celestial bodies, although relatively close in space, can actually belong to two completely different superclusters, having destinies that move in opposite directions. By the way, it's amusing to think that, because of its position, our Milky Way, a tiny, insignificant dot, located on the outskirts of Laniakea, in a remote region with a volume of about 500 million light-years in diameter, it is extremely close, on the cosmic scale, to another great basin of attraction, that of Perseus, shown here in red. And we missed being gravitationally bound to the latter by just a few tens of millions of light-years. When looking at these flow lines and galactic currents, one might be tempted to imagine the galaxies in this gigantic structure as all being gravitationally bound to each other and therefore destined to share a common fate. Indeed, these images of lines converging and plunging, as if siphoned in the same direction, suggest that the hundreds of thousands of galaxies in Laniakea will, in the distant future, all cluster together, sliding to the same place. At a sort of lowest topographical point on the map, where there is a mysterious and disturbing region, which we have already discussed at length in a previous episode, and named the Great Attractor. But strangely enough, that's not really the case. Because all these galaxies in Laniakea, which seem to be swept along by the same current toward a turbulent center, are actually connected only by a network as fragile as the wind. And in a few tens of billions of years, the acceleration of the expansion of the universe will most likely tear apart this fantastic galactic arrangement from within, unraveling the tenuous threads that connect them, woven together by gravity. Today, we only have measurements for 20% of the galaxies located within 400 million light-years of us, and almost none beyond that. And in terms of volume, we have so far only covered 1/1,000,000th of the observable universe. Drawing the universe, sketching the portrait of the greatest thing, the one that encompasses us all, is an adventure that's only just beginning. Because trying to map galactic flows is an immense task, just like what it allows us to study, the undefined boundaries of a dizzying geography of infinity. And not content with revealing to us the presence of structures whose very existence feels like giant candy to my soul, the study of matter on the large scales of the universe allows us to learn more about the hidden distribution of a mysterious, invisible substance, which physicists believe makes up nearly 80% of the matter in the cosmos. Dark matter, which we are not able to see directly, but whose presence is revealed by the gravitational influence it exerts on the distribution and dynamics of galactic flows. In the meantime, here we are, slowly drifting in a remote province on the outskirts of what has become the second-to-last line of our cosmic address. After Laniakea, are there still lines left to write? Even larger structures to describe? For now, we don't know. One thing is certain, there's still a lot of fog to clear before we can hope to erase all the terra incognita from the map. As we wait to hopefully see things more clearly one day, here's something to guide you if you ever feel lost. The precise address for all of humanity: Earth, the third planet from the Sun, local interstellar cloud, 50 light-years from the main plane of the disk, and 27,000 from the center of the drain. Galactic, inner part of the third spiral arm, Orion spiral arm, outskirts of the galaxy, Milky Way, local group, local galactic cluster, Virgo Supercluster, Laniakea, in the observable universe. The last line of our cosmic address, the boundary beyond which, visually, known things stop, because the light beyond its limits hasn't had time to reach us yet. But beyond that, obviously the map, the overwhelming geography of the entire universe continues. Because we haven't reached a limit there, an impassable boundary. And maybe the immensity within, already incredibly difficult to grasp, is itself ridiculously small compared to what remains to be mapped if we consider the entire universe. Let us imagine the map outside the frame. And while we wait to maybe one day find out what's hiding beyond, you can follow me on Insta or support the channel through Utip, TP, or the join button. Well, only in this observable universe.